Thanks for the introduction. Okay, you should prepare yourselves for a lack of rigour, which will probably horrify and surprise most of you. Let's start with a brief motivation. So there's lots of reasons to be interested in quantum field theory on fixed curved backgrounds. If those backgrounds are electromagnetic, then I might use them to study intense laser physics and the intensity frontier of the standard model. If I've got magnetic fields, I can look at the phase diagram of QCD or magnetar environments in astrophysics. The color glass condensate is another area where strong classical fields of glue turn up. Look at particle dynamics in gravitational backgrounds. And a particular interest for me is the study of physics on fields which are strong, which just means that they are characterized by some dimensionless coupling, which is larger than unity, and which you can't treat in perturbation theory. And we're going to look at some, but not all, of these topics today. So here's an outline. I'm going to start off in QED, looking at essentially intense lasers. Very briefly talk about the extension of these ideas to Yang-Mills. And then finally we'll talk about gravity, focusing on double copy and the extraction of classical observables from quantum amplitudes. Details are going to be really minimal. This is a bit of an overview of what I and my collaborators have been doing the past few years. The unifying theme behind these topics is going to be the type of backgrounds that we consider, which in some sense are going to be the same in electromagnetism, in Yang-Mills, and in gravity. Okay, so let's start with QED. And let's consider a laser electron collision. So I take my laser, I fire it at some electrons. Now, a modern laser will deliver photons of energy roughly 1 eV into spot sizes measured in microns over a duration measured in femtoseconds. And what this means is that you have a huge flux of photons or a very high intensity. Now, if these numbers don't mean much to you, don't worry. They don't mean a great deal to me either. So let's introduce a nice dimensionless parameter. This guy A0 is called the dimensionless intensity parameter. It's given by the charge mass ratio of the electron, that's E over m, multiplied by the electric field strength of my laser, that's big E, divided by the frequency omega. And the point is that due to chirp pulse amplification, which won the Nobel Prize in 2018, we can these days reach an intensity parameter A0, which is much larger than 1. Okay, so what does that mean? What is the physics of the statement A0 is much larger than 1? If I take this parameter and I rewrite it in terms of the laser wavelength lambda, then A0 is just the ratio of the work done on an electron over the laser wavelength divided by the rest mass. So when this exceeds unity, electrons are accelerated to relativistic velocities over a single laser wavelength. So we're doing relativistic physics. If I play the same game, but rewrite my A0 parameter in terms of the Compton wavelength, lambda c, then A0 is the work done over a Compton wavelength divided by the typical energy of photons in the laser. So when it exceeds unity, you've got multi-photon physics, which is essentially nonlinear physics. And finally, as we'll see again on the next slide, it turns out that A0 is actually the coupling of the laser to matter. You might think, I'm doing electrodynamics, the coupling is alpha, or root alpha, the charge. The coupling to a strong laser field is not alpha, it's this thing A0. And when this becomes larger than 1, you've got relativistic, nonlinear, and non-perturbative physics. Okay, so, given that, how do I do calculations in such a regime? Let's go back to basics. There's the Lagrangian of QED. The first two terms are the free theory. The third term is the usual interaction. And the fourth term is a kind of copy of that interaction in which I've introduced a background field, ABG, which is supposed to describe my laser or some other external classical field that I'm interested in. If I take this guy, ABG, divided by the rest mass of the electron, then it will be characterized by some dimensionless quantity, and that's my A0. Right? So whenever you see ABG, think of it as A0. It's a big number. Okay, so how do I calculate with this Lagrangian? Well, I'm going to do something completely trivial. I'm just going to reorganize the terms in that Lagrangian as such. What I've done is move the background field terms into the quadratic parts of the action. Right? So this defines, well, this tells you how to calculate. This defines something called the Fourier expansion. You might also know it as background field perturbation theory. So this guy A background, that's characterized by some big number. I can't treat it in perturbation theory. So what I've done is I've put it into the free part here, and I'm going to treat it without approximation, so that when I write down my Feynman rules, what happens is that my propagator is not the usual propagator, the inverse of the Dirac operator. It's now the inverse of the Dirac operator in this background field, and we draw that with a double line. The final term I Lagrangian, the one in red, is just the usual interaction term that describes interactions between kind of dynamically generated and absorbed electrons, positrons, and photons. Those interactions are still characterized by alpha, or root alpha, right? That's still a small parameter. So I've got the same interaction vertex, and I've got the same, essentially, loop expansion as in ordinary perturbative QED. So if I use this expansion, I'm treating the background field, the strong background field exactly, and I'm treating weak interactions, not actually weak, but not strong interactions in perturbation theory, as you'd expect. Well, that all sounds fine. I've basically given you the Feynman rules. Can we go away and calculate anything? Well, unfortunately, there's no free lunch, because if you give me a background field, say, okay, I want to study physics in this background, then I cannot give you back this all-important double line, right? Because it involves inverting the Dirac operator in a background, and we can't do this exactly. We can do it in perturbation theory, but that's not relevant if the background is strong, right? It's not going to give you meaningful answers. And of course, the reason that this is difficult is that by introducing a background, you've introduced preferred directions and so on, and you've lost a lot of symmetry. So you're dead in the water at the start. And one way out of this is to look for examples, simple examples of backgrounds which capture some of the physics that you're interested in, but which still allow you to make some analytic progress and gain insight. And the canonical example, at least in QED, is to study physics in plane wave backgrounds. So let me tell you what a plane wave is. Plane wave is a vacuum solution of Maxwell equations and later on the Einstein equations. The gauge potential is shown on the top left. So the capital E here, that's a two-component vector, describes the electric field of my laser, say, and I choose that to look a bit like the wiggly red line. So it's turned off, wiggles a bit, turns off again. It looks like a pulse of light. I'm working in light front coordinates, flat space, but light front coordinates. So my x plus and minus are t plus and minus z, and my xa's are what's called the transverse coordinates. That's just x and y. So my gauge potential is a function of x minus, which means it describes something traveling at the speed of light in the z direction. Yeah. It's a pulse of light. Now, plane waves are lovely for a lot of reasons. They're highly symmetric, or they've all got a 5-dimensional isometry group. They don't create particles on their own, so the vacuum is stable. There's a well-defined S matrix, and my spacetime splits up into nice in and out regions where I can do scattering. Yeah. The key point is that this propagator we need, this double line, that is known exactly for all plane waves, which means I can go away, write down my Feynman diagrams, and actually calculate them. I can do stuff. Of course, this is not as straightforward as calculating in vacuum. Some of the things that happen are kind of physical and interesting. So, for example, when you scatter in a plane wave, there are memory effects. So a particle comes in, it goes across the wave, it goes out, and it retains a memory. It knows that it crossed that wave, and this is encoded in position and velocity memory effects. So there's some interesting physics. There's also some complications. Because I've introduced a function which depends on the space-time direction x minus, I'm obviously going to lose overall momentum conservation in that direction. And the loss of just one momentum conservation rule makes calculations much more complicated than in vacuum. And finally, the eagle-eyed amongst you may spot that the fields of this plane wave are, of course, infinitely extended in the transverse directions, the directions transverse to its direction. So it doesn't sound very much like, say, a focused laser pulse. Right? If you've got a laser pointer in front of you, this doesn't look much like a beam of light because it's infinitely extended. Well, including laser focusing analytically is a very hard problem. We can do it numerically, but we're not going to touch that today. For us, our plane wave model is going to be good enough. So just to give you kind of a hint of the differences between doing scattering in vacuum and scattering in plane waves, let me just flash up a couple of equations. So imagine that we're doing scattering in vacuum just for a second. How do I describe an electron coming in with momentum p? Well, it's just described by a wave function e to the minus I p dot x, right? And let's ignore spin. Okay. So if I scatter on a plane wave, yeah, well, my propagator, my wave functions, they have to describe the interaction of my particle with that wave. And so your e to the minus I p dot x becomes this guy, this Volkov wave function, as it's called. So it's still an exponential. It's still got a minus I p dot x in it, but it's also got a lot more structure. It's got terms which are both linear and quadratic in what's called A. A is just the integral of the electric field of the plane wave. Okay, so there's my background. This is nice and compact. It looks fairly simple. In fact, it contains a huge amount of structure because what this really describes is an electron coming in, absorbing arbitrarily many photons from my laser, from my plane wave, and then re-emitting them again. So it's a sum of an infinite number of Feynman diagrams that happens to resum into this tidy exponential form. But okay, you've got this guy now. You can go away and you can start calculating things with it. And just to illustrate, here's an example calculation that you can do. Imagine that you take a photon, and you throw a photon into this plane wave background, and it creates an electron-positron pair. This is called nonlinear Breit-Wheeler. Yeah. And what's written on the slide is the total probability of this nonlinear Breit-Wheeler pair production. I've chosen a particular plane wave background to make my life simple. I've taken this to be the impulsive limit of a plane wave, in which I've shrunk the duration down to 0 while keeping the work done, that's A naught, constant. Yeah? So it's a delta function limit. This is just to show you a closed form expression. Yeah? It's a total probability. It's perturbative in the fine structure constant alpha, yeah? Because there is, if you can see my mouse, there's one vertex. Yeah? But it's clearly not perturbative in the coupling to the background, that's A naught. Yeah? This is not a perturbative expression. This is clearly all orders in the background. On the bottom right, there's a plot of this probability. That's this curve here, compared to the perturbative prediction, which just shoots up and of course goes wrong as soon as A naught goes above unity. Now, you wouldn't want to use this impulsive model to actually go away and compare with experiments. Right? A real laser pulse is not impulsive. It has a definite duration, and that duration matters. But just keep this plot in your heads for a second. Right? The exact result is a curve. The perturbative result is roughly a straight line. Keep that in your head. As we go to the next slide, which I want to tell you about a planned experiment which seeks to measure this nonlinear Breit-Wheeler process. So, in the mid-90s, there was a landmark experiment at the SLAC facility, the E144 experiment, where they did exactly this. They generated high-energy photons, collided those photons with a laser, and observed the production of electron-positron pairs, okay? Light into matter. But that experiment was weak field, so their A naught was essentially smaller than unity. And what the Luxy experiment at Dacey in Hamburg wants to do is measure, the corresponding strong field process or intense field process. So this plot is a little bit like the one on the previous slide, except this is all done with more realistic parameters. That's not important. All we need to know is that this plot shows you the number of pairs produced per photon that you send in to collide with your laser as a function of that laser intensity A naught. The SLAC experiment is shown on the left. Get that it was perturbative. And the two curves that are shown here, the dashed straight line, that's the perturbative prediction for the number of pairs. And the curved line, that is the all orders prediction for the number of pairs. SLAC was perturbative, What Luxy wants to do is actually measure this curve, the bending of the curve, and see the onset of these non-relativistic, non-linear, non-perturbative effects in QED. And hopefully that experiment will hopefully be going ahead, well, in the next 5 years or so. And there are many places around the world, there are lots of laser facilities in planning and in construction which want to measure similar effects in QED. But let me tell you about an experiment that's already been done. So a few years ago at the Gemini laser in the UK, we looked at laser electron collisions, and we measured both the energy of the photons that were emitted from that laser, from the electron as it was shaken around by the laser, and also the energy which the electrons lost as they went through the experiment. So what we're really measuring, and what we were measuring, of course, is self-force, also called radiation reaction. So here are some of the diagrams that kind of contributed to the experimental, which are contributing to the process of interest, right? So that first diagram is just our double line, our propagator. What does that describe? Well, remember I said that this encodes the interaction with the background. So all this does is it describes the Lorentz force of an electron as it goes through the laser, as it goes through my plane wave. Right? Now, if you just take your theory predictions based on that diagram and you compare with the experiment, it's way off. Right? Completely wrong, so something else is going on. And what else is going on is described by the other diagrams on the slide. So in the middle line, you've got this 3-point guy. That's the electron going into the laser, emitting a photon. That's radiation. But this diagram also contains momentum conservation, so it contains radiation reaction. And at the same level, in the Fourier expansion, or the background field perturbation theory, you have this interference term between tree level and one loop diagrams, and this also contributes to radiation reaction, or self-force. Now, if you include all these quantum effects, then you find that the experimental results are in much better agreement. Right? So essentially the results are consistent with the quantum theory. And we're now at the stage where we can use intense lasers to measure these kind of non-relativistic, non-linear, non-perturbative, and quantum effects in laser-matter interactions. One more on the QED side of things. So previously we said, if I send a photon into a laser, it might create an electron-positron pair. Well, if that photon doesn't have enough energy, then it won't, essentially, but something else can happen. So let's imagine that I take a beam of photons and I fire them into a laser. So I'm doing laser-laser collisions. One guy is strong laser field, and another guy is some kind of weak laser, it's a probe. And if I send this probe in with a linear polarization, it interacts with the laser, and what can happen is that it will emerge with a slight elliptical polarization. And this might remind you of something in optics. Spoilers, it's written on the top of the slide. This reminds you of vacuum birefringence. Sorry, this might remind you of birefringence, right? It's like you send a beam of light into a birefringent crystal and it emerges with a slight tilt in its polarization. And that's exactly what's happening here. So it turns out, as I've been known for a long time, that if you expose the quantum vacuum to really intense light, then it acts like a birefringent medium. So if you send in a beam of linearly polarized photons, it will come out with a slight ellipticity. What's actually going on behind this, it's kind of like the microscopic, the fundamental physics, is captured by the one loop diagram on the slide, where photons come in with some polarization. They interact with virtual electron-positron pairs, which are excited by the strong field, and they leave with a different polarization. Now, to be a little bit more strict, what's really going on is that we have helicity flip in this background field. So if I'm in vacuum, and I have a photon of momentum, a certain momentum and a certain helicity, well, it just goes on and it keeps that momentum and it keeps the same helicity forever. Right? They're conserved. But if it crosses a patch of intense field, then its helicity can flip. And there's a really nice relationship between the microscopic physics, this helicity flip, and the actual thing that you would measure in an experiment, the macroscopic physics. So what you measure in the experiment is the ellipticity induced in a probe beam of photons, right? Or strictly speaking, you would measure like the ratio of the intensities in two polarization directions. So you'd measure the ellipticity squared. And the relationship between the microscopic and the macroscopic physics is just that this ellipticity squared that you would really measure is exactly equal to the helicity flip amplitude mod squared. So that's the microscopic stuff, that's the macroscopic. Now, over the past, say, 10 years ago, the study of how to actually measure this vacuum birefringence phenomenon has really become a bit of an industry, and it's been chosen as a flagship experiment for the HIBEF consortium, also at DAISY in Hamburg. For measurements, again, hopefully within the next few years. Okay, that's all I'm going to say about QED. I'm going to move on to Yang-Mills, but only briefly. So, using this plane wave model, we can study electrodynamics in strong background fields, strong plane waves. And you might ask, well, can we do something similar in Yang-Mills? And the answer is that yes, and you can do quite a lot. So let's stick with our plane wave model. And the first thing that we should ask ourselves is, what do we mean by a plane wave, a non-abelian plane wave, or a plane wave made out of glue, if you like? Well, what you really mean by that is a field which has exactly the same symmetries as all the other plane waves that you know, okay? And those would either be in electromagnetism or in gravity, where they have, and both electromagnetic and gravitational plane waves have the same five-dimensional isometry group. So if you ask for a non-abelian field with the same symmetries, then what you find is that it has to be valued in the Cartan of your gauge group. So here's a non-abelian plane wave. It has exactly the same structure as the electromagnetic guy, right? So I've got two components here of chromoelectric magnetic fields, and then I've got some generator in my Lie algebra, and that guy has to be Cartan valued. So what does that mean? What it means is that interactions of color-charged particles with this background are effectively abelian. Because my gauge field is in the Cartan, if I take the commutator with the generator of any charged particle, it's TC on the slide, that commutator is just the same as multiplying the generator by a scalar function. Q is the color charge of this guy. Okay. If you're not familiar with this stuff, it doesn't matter. All that matters is that this means that the interaction of color charged particles with a background is effectively abelian. It's effectively like QED. And what this allows you to do is to take a lot of techniques from QED and plane wave backgrounds and just transport them directly into Yang-Mills. Now again, it's not a free lunch, right? Because although the interaction with your background is effectively abelian, the interaction between particles that are scattering and generated and absorbed, that's still fully non-abelian. Okay? So things are, of course, more complicated, but you can still calculate things and generalize a lot of stuff from QED. Just as an example, I'm going to skip that slide for the sake of time. So for example, you can calculate helicity flip, like we just did in QED. You can calculate this in Yang-Mills theory, and you can calculate it in supersymmetric Yang-Mills theory. Some of the diagrams are shown at the top of the slide. So I'm sending in a gluon. It's scattering across a gluonic plane wave background, and it's emerging again. So I've got a gluon loop, I've got a ghost loop, I've got a gluon tadpole, I've got matter running in the loop. All of these guys, by the way, should be double lines because they're encoding the interaction with the background exactly, but it's really ugly if you try and draw it in QCD and Yang-Mills. Okay, so if I do this in Yang-Mills theory, then there is a gluon helicity flip amplitude, great. And if I do it in supersymmetric Yang-Mills theory, then I find that this helicity flip amplitude vanishes. This is true in n equals 1 SUSY QED and SUSY Yang-Mills. Which would mean that if we lived in a world with unbroken SUSY, there would be no vacuum birefringence on any kind of plane wave background. So this is a result which was previously known in the kind of weak field Euler-Heisenberg limit, constant fields essentially. But it's actually true for any plane wave. So no matter what energy I have for my gluon probe, no matter what energy I put into my plane wave, no matter what shape or size or duration or strength it has, there's no helicity flip and no vacuum birefringence. And it's quite nice that you can see this just by essentially brute forcing the calculation, because there is no reason to expect this. Right? A plane wave is not a supersymmetric background. So there's no kind of obvious Ward identity which says, you must conserve helicity when you scatter on a plane wave. Right? But it turns out you do. Helicity is still conserved, like it is in vacuum. So this is just to illustrate that you can do calculations in Yang-Mills on gluonic backgrounds, and you can get some new results. I'm just going to go straight on to gravity. And I want to start by talking about double copy. So this is a lightning fast introduction to double copy, or color kinematic duality. So what is double copy? Let's go back into vacuum now. There's no backgrounds, there's no background fields. Double copy says that if I take an n gluon scattering amplitude, calculated in Yang-Mills theory, and I pull off all the delta functions, which conserve overall momentum, and I pull off all the color factors as well, and I square what is left, then what I get is a scattering amplitude in gravity. I get an n graviton scattering amplitude. So this goes by the kind of the pithy name of gravity is gauge theory squared, and there's an example relationship shown on the slide. So M4 is the 4 graviton scattering amplitude at tree level. So I've got gravitons 1 and 2 going to gravitons 3 and 4. And that is given by taking the 4-point Yang-Mills amplitude, squaring it, and then multiplying it by this combination of the Mandel-Stam variables S, T, and U. Okay, so up to factors, gravity is Yang-Mills squared. And these relationships persist to all n at tree level, and they've also withstood every test that you can throw at them at loop level so far. So what this says is that there is a really interesting connection between Yang-Mills theory, in some sense squared, and gravity. There's something going on there. But all of this, of course, is essentially doing perturbation theory around a flat background, around a flat spacetime. And the natural question to ask is, well, if these kind of double copy relations are really pointing at something fundamental, some fundamental relationship between gravity and Yang-Mills, then they should also persist if we do look at perturbation theory around a non-trivial or a curved background. And given what all the rest of the talk has been about, what we're going to look at is scattering on plane wave backgrounds and see if there is a double copy there. Okay, so let's start with gravitational plane waves. There's the metric for a gravitational plane wave in Brinkmann coordinates. I'm sticking to 4 dimensions. The first 2 terms in black are just Minkowski space in light-front coordinates, and then the final term in blue, that's the interesting stuff, that describes my plane wave. Yeah. As before, XA is a 2-dimensional transverse vector, and HAB on this slide is a 2x2 symmetric traceless matrix. So it has 2 functional degrees of freedom. It contains 2 functions of x minus, just like a gauge theory plane wave has 2 electric field components. Right? This is a solution of the Einstein equations. It's not asymptotically flat, but it's not flat only in one direction. So I've still got kind of, if I look at my toy space-time diagram down here, I've got nicely separated in and out regions. I can do scattering on this background. Again, there's no particle production. And these backgrounds share all the same symmetries, the 5-dimensional isometry group, with their abelian counterparts. These symmetries are not manifest in Brinkmann coordinates, which means the calculations are a little bit clumsy. But the point is that just like in QED and Yang-Mills, I know how to write down my propagators for particles on this spacetime. I know how to write down the equivalent of those Volkov wave functions that we have, which describe in and out states. And I can do this for scalars, and for gluons, and for gravitons, and I can go away and calculate. So, I can calculate scattering amplitudes on this background. I can calculate scattering amplitudes on a Yang-Mills background. Sorry, Yang-Mills scattering amplitudes on a Yang-Mills plane wave background. Is there any kind of relationship between them? Well, we're going to look at the simplest kind of amplitudes that you could possibly calculate, almost 3-point amplitudes on our backgrounds. So, again, in vacuum, in flat space, the double copy says that the 3 graviton amplitude, suitably continued off shell so that it makes sense, is literally just the square of the 3 gluon amplitude in Yang-Mills. Okay, so there's this relation M3, that's gravity, is A3 squared. Okay, so now I do my Yang-Mills calculation on my gluonic plane wave background. What do I get? Well, the 3-point amplitude looks like this guy. You've got 3 momentum conserving delta functions. Yeah, remember we said we always lose one when scattering on a plane wave background. I've got some color factors, and I've got an integral over kind of a non-trivial direction on which my plane wave depends. Sorry, there's an exponential factor and there's a pre-exponential function. Okay, so what am I supposed to do with this? Because the double copy relations tell me that I'm supposed to strip off, you know, the usual 4-dimensional delta function, but I don't have that here. Well, if you stare at this, you realize that if you turned off the plane wave background, then this exponential part over here would just reduce to the usual kind of e to the I p dot x kind of terms that you get in any scattering calculation. And the combination of this integral and that exponential would reproduce the missing delta function. So what you should do, it turns off, is actually strip away the delta functions, the integral, and the exponential, and just focus on what's left. Okay, on this function I3, which, you know, is a complicated thing, but we don't need the details. Then what you can do is you can establish a double copy map, which takes this integrand, I3, squares it, makes some transformations, and this gives you exactly the corresponding integrand for the 3 graviton amplitude, where you've gravitons are scattering on a gravitational plane wave background. So you can establish a double copy map, and what you're finding is that this is acting in position space, right? Not in momentum space, but in position space. And once you've established this guy, you can go away and then you can test your prescription by calculating other amplitudes. You can go to higher points, 4-point amplitudes in gravity and in Yang-Mills. And you find the double copy prescription still holds, and you can even go to lower point amplitudes. Let's go to 2 points, which describes memory effects of particles crossing these gravitational and gluonic waves. And you find that having the double copy acting in position space is crucial if you want to recover like known classical memory effects. So there is still something going on. Even if I introduce a non-trivial background in gravity or in Yang-Mills, I still find there is some kind of relationship between the scattering amplitudes in the gauge theory and the scattering amplitudes in gravity. Now, I think it's fair to say that double copy is not entirely understood still, right? We don't really understand the fundamentals of why it's there, and as a result, there are different prescriptions for how you might do double copy or what it might mean. So I'm going to look at a slightly different one. Let's go back to classical physics. I've got my gravitational plane wave, I send in a particle, I can ask how does it move? I can calculate the geodesics. And a few years back there was quite some interest in a particular class of plane waves which have, as well as the usual 5 isometries that any plane wave has, they have an additional 6th helical symmetry or screw symmetry. Okay, so these guys are somehow very, very symmetric. They're waves, they're propagating along, and they're also kind of rotating as they do it. Because of this high degree of symmetry, you can solve the geodesic equations and you can just plot the orbits, and here's an example. Okay. So on the left is a particle orbit, massive particle orbit in one of these screw symmetric plane waves. The left-hand plot shows you the orbit projected into the transverse plane, so that's the plane kind of transverse to the direction of motion. And on the right-hand side, I've just tilted the view so you can also see the motion in the longitudinal direction, the same direction as the wave is propagating in, which of course is our light front x minus direction. Okay, great. So what? Well, you stare at these orbits and then you realize that actually they're very similar to orbits in a certain electromagnetic background, and it's not a plane wave. These orbits are very similar to those in what's called an electromagnetic vortex, and that's the difference. I'm just going to flick back and forward a second. So an electromagnetic vortex is exactly what it sounds like. It's some kind of swirling vortex of rotating electric and magnetic fields. And the orbits in this guy can also be calculated. And in the transverse plane, they are identical to the orbits in the gravitational field. In the longitudinal direction, they're different, right? That's gravity, that's complicated. That's electrodynamics, that's a bit less complicated. So what's going on? We said on the previous slide that plane waves were related to plane waves via this double copy thing. But here we've got plane waves in gravity being related to a different kind of field, a vortex, which is not a plane wave in electrodynamics. Well, it turns out that this is an example of what's called Kerr-Schild double copy, classical double copy. And very, very roughly, skipping all the details, what this says is that if I have a scalar function which obeys the wave equation, roughly, then I can generate from this a gauge field which obeys Maxwell's equations, and I can generate a metric which obeys Einstein's equations, just by taking my scalar field and multiplying it by a null vector n. So for our gauge field, that's bad. This gauge field points in the x minus direction, for our plane wave. And if I take my scalar field here to be this combination of the transverse coordinates and the metric function h, which appears in the gravitational plane wave, then of course I get the metric for a gravitational plane wave, but the gauge field is not a plane wave, it's this vortex. So the reason that these orbits are so similar is that it's because the backgrounds that they're moving in are related by this Kerr-Schild double copy, which maps solutions in gauge theory of Maxwell's equations to solutions of Einstein's equations. So take home is gravitational plane wave with screw symmetry is a double copy of this vortex in some sense. Okay, so safe to say there's still plenty to understand about kind of how these different versions of double copy are related, which if any are the more fundamental, and so on. Let's move on from double copy and look very quickly at the Amplitudes program. So there's been a lot of work throughout this talk. We've been looking at scattering amplitudes, right? There's been a lot of work in the amplitudes community over the past few years on extracting classical gravitational observables from the limit of quantum scattering amplitudes. And you might think, why? Why would you want to do this, right? Well, it turns out that sometimes doing a quantum calculation and then taking the h bar goes to zero limit to get the classical result is a lot simpler than doing the classical calculation by brute force. And the application to gravity, which that community has been focusing on, is essentially the two-body problem, right? So you imagine two bodies, two massive bodies orbiting each other. Their momentum is changing, they're radiating gravitational waves, and of course you might want to measure those gravitational waves because that's exactly what you want to do in gravitational wave astronomy. Yeah? And the idea is to try and calculate observables related to this two-body problem from the classical limit of quantum field theory. And of course, let's play the same game, that's all been done in flat space. Yeah? You could also ask, well, rather than study the two-body problem, what about the one-body problem, essentially? Right, take some particle, it crosses a gravitational field, it comes out with a kick in its momentum, it emits some gravitational radiation, and I want to measure this guy. So what we're really asking is, can I calculate classical observables on curved backgrounds from the limit of quantum scattering calculations on those curved backgrounds? The answer is yes, we can. This is a program which we've recently started up in Edinburgh. Just as a very quick example, suppose you take a particle, it crosses the gravitational background, its momentum changes. How do you get that? Well, what do you mean by momentum? In quantum mechanics, you mean the expectation value of the momentum operator. You can calculate this guy in the final state. Yeah, the final state is just the S matrix acting on the initial state. You can express this in terms of amplitudes and take the classical limit. What you find at the lowest order of background field perturbation theory is that this momentum is supported on the 2-point amplitude in your background. What is the 2-point amplitude? It's essentially just the propagator. Yeah. And I said, of course, that we can construct this propagator in plane waves. So you can write this guy down, you can take the classical limit and show that indeed you get very easy access to memory effects, classical memory effects. And we can do this in plane waves, we can do it in shock waves, and in some approximation we can do it in more complicated spacetimes like Schwarzschild. If we go to higher points, then we can start adding radiation reaction and self-force contributions to these observables, and that is work in progress. I can see that I'm over my time, so I'm going to finish there. I'll flash up the conclusions and let you read them in your own time. Thank you.